Hello everyone, welcome to GATE Pass. So in this video, I am going to take two problems that appeared in GATE 2015 and which were related to thermodynamics. So this problem was question number 14 and it is again based on chemical reaction equilibrium. So you will observe that this is the 8th year which we are solving. Okay, this is 4th time when your question on chemical reaction equilibrium is appearing. So you should keep this in mind that this is a very important topic, and in 2021 and 2022 no question related to chemical reaction equilibrium appeared. So it's high time that you may see it in coming years. Okay. So let's go through the problem first. There is a gas phase cracking reaction in which A is cracking into B and C at 300 degrees centigrade and pressure of 1 bar. Okay, delta G0 is given and they have asked you to assume a ideal gas phase, and you have to calculate your fractional molar conversion of A at equilibrium. Now no data is given about the number of moles. Okay, so we will assume a basis, and what basis we will assume is that let's take 1 mole of A is reacting. Okay, so I am going to take 1 mole of A is reacting and initially no B or C is present. Fine. Now you have seen these equations, so I have told you that you can solve this type of question in 3 steps. Okay, so the first step will be you have been given delta G0 and you have to calculate your K, that is the equilibrium constant. So your first step should be to quickly calculate your value of K. Okay, so that we are going to do first. So your K, that is equal to exponent minus delta G0 by RT. Okay, so put the values. Delta G0, that is minus 2750 minus plus, so 2750 upon 8.314 into T. Now be careful at this point. Don't make a mistake of putting 300 over here, because I have told you several times, whenever you are using equations, unless and until it is specified, you should convert all your temperatures into your Kelvin, in your Kelvin scale. Okay, on your Kelvin scale. So I am going to convert this 300 degrees to centigrade to Kelvin. That will be 573. So I will multiply with 573. So what I get is that exponent of, if you solve this, I have a value which is equal to 0.577, and that is equal to 1.781. Okay, so you have calculated the value of K, which I will retain on the board. Other things, because this is a very common equation, I am going to erase it. So I will write down 1.781. That is your value of K. Okay, what was the second step? Now I have asked you to remember this equation for a gas phase reaction. Okay, the second step was to simplify this equation. So they have asked you to assume an ideal gas phase. So phi I cap, that is equal to 1. The given pressure is 1 bar. Your standard pressure P naught is 1 bar. So this cancels. So what you are left with is essentially product over all I, yi raised to nu I, that is equal to K. Okay. Now, how do you find your yi in terms of your extent of reaction, which I am referring to as epsilon? Okay, that is Ni0, that is the initial number of moles of ith component, plus nu I, that is the stoichiometric coefficient of that particular species I, multiplied with the extent of reaction. This gives you the number of moles, okay, at any time, and the initial and the total number of moles is given by N0 plus nu times epsilon, when nu is nothing but summation of all nu I. So first let's calculate what is summation of all nu I. That is equal to minus 1 plus 1 plus 1. So that is equal to 1. So my nu is 1. Now I am going to write down my YA, YB and YC in terms of my extent of reaction. Okay, so that's also a very straightforward step. Ni0 since for A I am taking Ni0 as 1, so 1 minus mu I, that is for A is minus 1, so minus epsilon upon initial number of moles 1 plus summation of all mu I is 1, so plus epsilon. Okay. Similarly, I am going to write epsilon upon 1 plus epsilon, epsilon upon 1 plus epsilon. We can check quickly if I am right. Okay. Now what I am going to do is put these values in this equation and do the calculation. So it's very simple. Okay. So what I get from here, yi raised to nu I. Okay. So all the products, they will be raised to a power of 1. So they will come in the numerator. So epsilon upon 1 plus epsilon multiplied with epsilon upon 1 plus epsilon divided by, this is the reactant, so 1 minus epsilon upon 1 plus epsilon. Okay. One of these will cancel, epsilon times epsilon, that is equal to epsilon square. 1 plus epsilon into 1 minus epsilon, that will appear in the denominator. So a plus b into a minus b is a square minus b square. So I can write 1 minus epsilon square, that is equal to k. Okay. Now I will erase this so that I get some space on board. So you have epsilon square is equal to, I will take it over here, k minus k epsilon square, or if I add bring it over here epsilon square and take the coefficients in the bracket, then I have this thing. So what is epsilon? That is k upon 1 plus k, the whole thing under root. Okay. So what is k? 1.781 divided by 1 plus 1.781, 2.781. If you do this, you will get the value of 0.8. Okay. So your extent of reaction is 0.8. Now they have asked you to calculate the fractional conversion. What is the definition of fractional conversion? Fractional conversion, if I say, that is F, that is defined as initial number of moles of A minus the final number of moles of A divided by the initial number of moles of A. Okay. Initial number of moles is 1. What is Na? 1 minus 0.8. So that is Na is 0.2. So 1 minus 0.2 upon 1. So that is equal to 0.8. So your fractional conversion is 0.8, which if you solve these problems, you can directly write from here as well, because you are starting with only 1 mole of reactant. Okay. So this was a very straightforward problem. I have told you tackle this problem in 3 steps so as to quickly solve this problem. So the next problem which I am going to take is question number 31. In this you have an ideal gas which is going through first an adiabatic process and then an isobaric process. Okay. So let's go through the problem. So you have an ideal gas which is initially at a pressure P1 equal to 0.1 megapascal and a volume of 2 meter cube. It is compressed by a reversible adiabatic process to P2 equal to 1 megapascal and V2 is not given. Okay. Then it is compressed at a constant pressure to a final volume of 0.2 meter cube, and your final pressure will be same as 1 megapascal because it's a constant pressure process. Okay. The value of R is given and further Cp is given as, that is equal to 2.5 R. Okay. So now they have asked you to calculate what is the total work done on the gas in kilojoules for this entire process. Okay. Let's first calculate what will be the work done for this process. So I am going to write my first law, that is change in internal energy, that is equal to Q plus W. Okay. Now this is an adiabatic process, so Q is equal to 0. My sign convention is that the heat going into the system is positive and work done on the system is positive. That's why a positive sign comes over here. So you have delta U is equal to W. That will be equal to, for ideal gas, you know the delta U, that is equal to Cv delta T, and in this case it will be T2 minus T1. Okay. Since these quantities are not molar quantities, so I should also keep in mind that I have to multiply it with the number of moles. Okay. So your work done that is equal to the change in the internal energy, and that is equal to NCV T2 minus T1. Okay. Now let's simplify this equation in order to use it. Fine. So let's say we are not given the value of CV. So first we will find that. So your Cp minus Cv, that is equal to R, but your Cp is given as 2.5 R. So then I can calculate my Cv, that will be equal to 1.5 R. So I can also calculate my gamma, okay, that will be equal to Cp by Cv, that is equal to 2.5 upon 1.5, or I can write it as 5 by 3. You have calculated what is your Cv and what is your gamma. Okay. Further, you know that because this is an adiabatic process, then I can write P1 V1 raised to gamma, that is equal to P2 V2 raised to gamma. Okay. So this equation I am going to use to find out my V2. Okay. So let's rearrange this equation. So it will be P1 by P2, that is equal to V2 by V1 raised to gamma. If I take gamma over this side, it will be 1 upon gamma. If I take V1 on this side, in order to calculate my V2, okay, so I get the equation, put everything over here and find V2. So V1 is 2, P1 is 0.1, P2 is 1, so 0.1 upon 1 raised to gamma, 1 upon gamma, okay. So your gamma is 5 by 3, so 1 upon gamma will be 3 by 5. Do the calculation, you will get 0.5 meter cube. Okay. So I have got this, V2 is 0.5 meter cube. Okay. Now let's come back to this equation. Since we do not know our Cv, T2 and T1, let's replace these values with the values which we know. Okay. So I am going to write N and Cv in terms of R. So I will write 1.5 times R T2 minus T1. Okay. Now I will take 1.5 outside and I will write NR T2 minus NR T1. From ideal gas law, you know that NR T2 will be equal to P2 V2 and NR T1 will be equal to P1 V1. So 1.5 times P2 V2 minus P1 V1. Okay. So put everything over there. What is P2? What is P2? That is 1 megapascal into 0.5 minus P1 is 0.1 multiplied with 2. Since it is megapascal, don't forget to multiply with 10 raised to 6. Simplify this. 1 into 0.5 is 0.5. 0.1 into 2 is 0.2. Okay, into 10 raised to 6. So what is 0.5 minus 0.2? That is 0.3. If you multiply it with 1.5, then you get the value as 0.45 into 10 raised to 6. This is in joules. Since they have asked you to calculate the work done in kilojoules, so I will write this as 450 kilojoules. Okay, so it was very simple. I could quickly calculate the work done in the adiabatic process. Now I will just erase everything because the work done for the constant pressure process is very simple. It will be given by, so let's say that this is the work done, that is equal to W1. So this is your W2, that will be equal to PdV work. So I have pressure which is constant, so it is minus P3, V3 minus V2. Okay, this is the work done in a constant pressure process. I have to just plug in all the values. So my P3 is 1 megapascal, so 10 raised to 6. V3 is 0.2 minus 0.5, and you have 0.3 into 10 raised to 6 joules, or I can write it in terms of kilojoules. Okay. So it was very simple. Now the total work done on the gas, that will be given by W, that is equal to W1 plus W2, that is in the adiabatic process plus the isobaric process. So it is 450 plus 300, that is equal to 750 kilojoules. Okay. So it was a very simple problem. Instead of using that big formula which is given in your book for the work done in an adiabatic process, what I have done is I have used my basic concepts of thermodynamics. So what I will suggest is that in thermodynamics, don't try to memorize all the formulas, just try to remember how these formulas come. Okay, if you try to emphasize on the concepts, then thermodynamics becomes very simple. So I hope you enjoyed this video and learned something from me. So if you like this video, please don't forget to subscribe to my channel and like this video, and thanks for watching.